it's time to kick off the latest edition, the latest episode of BS&BEER Canada. I don't think Justin is going to be able to introduce our handsome guest this evening, but I think we'll hand that off to Connor here in a second. But for those of you who don't know me, my name is Aaron Jones. I am a carpenter and a builder on Grand Manan Island, a closet blower door nut, building science enthusiast, and tonight I am drinking a blonde ale from Big Axe Brewery. And I'm going to hand this over to Jeremiah.
Good evening, everyone. I'm Jeremiah. I'm a builder and a learner in Southern Ontario. My brother and I own and operate a small six-person carpentry crew and focus on new construction and remodels, and really like to nerd out over building science and find ways to integrate interesting details that promote durability and healthy home concepts for our clients. And my beer fridge was completely empty, so I'm drinking a Canada Dry tonight. And I will pass this. Well, Justin out on the. All right, off to you, Connor.
Hey everybody, I'm Connor Malloy. I'm a designer, builder, and educator in Toronto. I teach carpentry students about best building practices when we're framing, learning how to build envelopes and enclosures, and how to manage air and keep water out. Big topics. Also do some consulting with builders and homeowners building high-performance homes and how to make sure we're sequencing things to build great enclosures. Tonight, I'm drinking Stay Classy. It's a non-alcoholic beer from Bellwoods Brewery from downtown. And I am also a blower door nut. I've been working on my latest project. This is a Lego scale blower door. And I'm not brand agnostic. We're working on a RetroTech door. Oh, yeah. Yeah. Only those in the room appreciate this. But I'm excited for tonight. I'm excited learning from colleagues. Matt is joining us tonight, is a professional engineer practicing in energy modeling, building envelope consulting, and mechanical design. He holds a Bachelor of Science in Environmental Systems Engineering and is a certified passive house consultant. He is the co-owner of Airtight Engineering and also teaches with Passive House Canada. In his free time, Matt enjoys ultimate frisbee, singing, and gardening with his wife. Matt, thanks for joining us. And what would you like to talk about tonight?
Okay, awesome. Thanks so much for having me. And I'm drinking Hit the Deck Hazy IPA from the Fernie Brewing Co. So that's my beverage of choice for the evening. And let me do a little screen share here. Get PowerPoint up for y'all. Okay. Someone want to give me a thumbs up if they can see a PowerPoint slide. Awesome. Amazing. So I do like long, wordy titles, so that's what I created for you today. So my presentation is called Things That Worked and Things That Didn't, High Performance Project Highlights. So I've got 5 themes that I want to talk about tonight. And this is going to be really high level, like what is some of the distilled essence of some of the lessons we've learned over the last few years working on some high performance projects across Western Canada predominantly. So that's what I'll be sharing with you tonight. There's a variety of topics. Let me start by just a little land acknowledgement. I'm on Treaty 4 territory here in Regina. And so I know that we're all spread over the country, but I'm in the homeland of the Cree, the Saulteaux, Dakota, Nakota, Lakota, and also the homeland of the Métis people as well. And it's a picture that one of my colleagues took. I think this is his farm. His farm is on Treaty 6 territory, but a pretty nice prairie golden hour photo for you. So here's my 5 themes that I want to talk about today. So first, client expectations. This is something that we've been learning lessons in, some the hard way in terms of building high performance, and people who are used to a certain type of building and are now living in or working in or occupying a different type of building. Because lots of us don't come from high performance buildings when we first buy a passive house or a tier 4, step 4 home, or step 5 or tier 5 home, or net zero, that type of thing. That hasn't been our experience necessarily in the buildings that we've grown up or worked and played in. The second thing I want to talk about is moisture in cold climates. Just a few interesting things that we've learned dealing with moisture in high performance homes in cold climates. Third, I want to talk about heat pumps. And then my last two topics are a little bit zoomy outy, kind of philosophical. The first one is not just good on paper. So how can I, as a designer and consultant, how do we translate things from like design into an actual good building? And then finally, how to think again. So some lessons that I've been learning very recently on changing or maybe not changing the way that I think about things, or helping other people change the way that they think about things, such as building science. So that's what I'm going to go for. And I tried something different. Usually I've got bullet points on my slides, and I made myself a challenge. I said, this is after hours. I'm drinking a beer. There are going to be no bullet points. Other than the 5 themes, you'll see no bullet points on my slide. So I hope it goes well. I hope it's not a terrible disaster. So you can be my guinea pigs on the no bullet point slide deck. So a little bit of context for where I'm coming from when we're talking about these 5 themes. So Airtight engineering, our big shtick is, can we marry envelope consulting and passive house principles with mechanical design? So as opposed to just being on the envelope side, as opposed to just being mechanical designers who sort of are handed in a building that they have to try to heat and cool, we try to integrate both of those on our projects and with our clients. So that's sort of behind, like we talk a lot about mechanical things, and you'll see lots of my examples are mechanically oriented, but we're always seeking to sort of marry that to the passive house principles. And the second context to give you is that we generally operate on the Canadian prairies. We do have some projects in BC. We have a few in Nunavut as well, but a lot of the projects that we do are in colder latitudes of Canada. So just some context for you there. So we got lots in Saskatchewan, some in Winnipeg, Alberta, etc. Okay, theme number 1 that I want to talk about is client expectations. This is let's do first example. This is a project that Justin knows, actually, and it's a project that we visited together a couple weeks ago. And it's a house in Saskatchewan, not too far outside Regina. And they've been having some troubles with cooling. And the owner of the house, his thermostat is set to 21 degrees, and his cooling system will only cool the house to 22 degrees. Now it's a heat pump, a water-based system, so it's an air-to-water heat pump, and we were trying to figure out what the issue was. But that's not what I want to focus in this particular example. It was very interesting that he wants his house to be at 21 degrees, even if it's 35 degrees outside. And that's like from a mechanical perspective, that's a pretty big ask. Like often we're designing cooling systems to keep houses at 22, maybe more like 24 in the old days. That was like the recommendation was peak conditions, you keep your house at 24. If your cooling system can do that, then it's good. But now there are clients who want their house to stay at 21 when it's 35 degrees outside. Versus another project, this one's in Canmore. This is a passive house project in Canmore. The glazing on the second floor there is facing due south, but it's very overglazed on the second floor. And something that I found fascinating when I was at this project last week with this gentleman who was concerned about his home overheating by kind of 1 degree above the set point was this Canmore house. The homeowner has like maybe 10 days a year where it gets really hot up there. So it's usually in the spring or the fall when you have that low south sun coming in that big glazed window. And the owner, so here's a picture of the finished house. It's a really beautiful view. And you can see the view from inside there, you can see the counter right here. Oh, maybe I can get my little pointer. Here's my pointer. So here's his kitchen island looking out through that south glazing. And we had a phone call. This was a couple of years after the house was finished. And this is something that we had raised when we were doing the energy modeling for this house, was we said, hey, look, you're doing really great in terms of meeting the passive house standard, but you're going to have a lot of troubles with overheating in that particular room just because it's quite overglazed compared to all the other rooms of the house. And they acknowledged that that was sort of a risk that they were willing to accept and went ahead and built the house. And his attitude, he has 10 days a year where it gets up to like 28 degrees in there. And he said, I'm okay with it. It's only 10 days a year. It's not a big deal. We just keep the butter in the fridge those days. We don't leave it on the counter. And that was his solution. He was happy with it. No more no more work needed on this particular project. So to me, this is a very interesting one example of how much the client's expectations make a difference in terms of some of these high performance projects, and whether something like overheating is a callback or whether it's just oh, here's a quirk of the house. So this is something that we've been trying to incorporate more into our practice, is doing a better job up front when we're designing a high performance home or consulting on a high performance home, of understanding what the client's requirements are. Like, are they going to be miffed if they're a degree off? And I'm saying that like no judgment. If you want your heating system to be able to cool to 21, that is a perfectly legitimate desire, right? And for some people, that's a make or break, and for others, it's not important. So just an interesting example of sort of how client preference drove one project to have some callback work required, another one to not have callback work required. Here's another example, a project that we worked on. This is a project in Saskatoon. It is not passive house certified, but it's pretty darn close. It would certainly be kind of tier 5 zone in terms of the energy code. And it's heated by this 1.5 ton Mitsubishi heat pump that I've got right here. And the client expectation that we could have communicated better on this one up front was how much their heating and cooling was going to cost. So the homeowner on this one assumed, hey, I'm going into a high performance home. It's super energy efficient. It's heated with this very tiny heat pump. I'm going to pay next to nothing on my energy bills. So they were very surprised when January rolled around and they had I think it was like a $400 bill for their electricity. And something that we had not done a very good job of communicating up front was the impact in Saskatchewan of switching from natural gas heating to electricity. And so on this project, their heat pump probably on average is like 200% efficient over the course of the year. However, natural gas is 7 times cheaper than electricity in Saskatchewan. So if you do the math, you're still paying 3.5 times as much for your energy if you're heating with an electric heat pump versus with natural gas. And they also weren't used to seeing heating and hot water on their electricity bill, right? They're used to that coming as a separate bill. So that, combined with the fact that there was a big polar vortex that January that was particularly crazy, which I have on a future slide, meant that they had a $400 electrical bill the first January that they're in the house. So that's something that we've learned in terms of high performance projects and customer expectation, is if we're fuel switching, making sure that we're being upfront with clients about what can you expect your energy bill to be. So the client was concerned that there was something wrong with the house, that the heating system wasn't working properly. And so we did some monitoring. We had an energy monitoring system put in. And here's some of the results that we got. So we did see that there was some fine tuning that could happen in terms of the heat pump. But overall, interesting that overall for the energy model, what we modeled and what we got for energy use was only 13% difference. So yes, there's some categories in here that were very different. So we noted that the heat pump was not running at full capacity and the backup heat was coming in sooner than it should have. We also noted that the heat pump was being used more for cooling than the model had shown it would be. So some of those things. But that ended up balancing out with some savings in their appliance use. And so overall, it was actually pretty close to what we thought it would be. And so it wasn't that the house wasn't working properly. It's just that we hadn't done a good job up front of setting that expectation with the client for what they could expect in terms of their energy bills. So that's something that we've learned with high performance homes and something that we're really clear with people at the outset about now. Of course, that your mileage may vary depending on where you are and what your power versus your natural gas or other fuel costs are. Another lesson that we've been learning recently is to communicate more with clients up front on what they're expecting in terms of controls and functionality with their heating and cooling system. So I come from the passive house world where our mantra is spend on the envelope so you can save on the mechanical system. So I think that's a really good idea. And that's kind of what I encourage. But it turns out that for some people, if you're building a very fancy custom home and it's going to be, maybe it's going to be net zero, maybe it's going to be passive, but it's a pretty expensive endeavor. Sometimes you have some pretty specific controls and zoning requirements too that you want to see in your project, even if me as the consultant from Passive House Land says, oh, you don't need any of those. So here's two projects, the mechanical room on the left and the mechanical room on the right. These are two different projects. One's in Saskatchewan, one's in second one's in Edmonton. And they're both very energy efficient projects. The one on the left is a much bigger house. But interestingly, the one on the left, they wanted a lot of zoning. So if you count our zone dampers here, got 1, 2, 3, 4, 5, 6, 7, 8, so we've 9. So we've got maybe 9 or 10 different zones on this house, even though it's quite a good envelope and the windows are low E coded. And so we don't expect there to be a lot of like hot spots or cold spots in the home. And yet it was important to this client that they had a lot of zoning in their home. Versus the house on the right, similar story, high performance home. And we started out with 2 zones in the house. We zoned the top 2 floors and we zoned the basement separately, just because sometimes you can get temperature stratification between upstairs and downstairs in the house. So we said, hey, we're gonna suggest that we zone this. And the client came back and said, actually, we don't want to zone it. We know there's going to be some temperature stratification. Let's not worry about it. We want the cost savings. And so, yeah, it was an interesting exercise for me to see how much 2 different clients, both building high performance homes, can have an impact on the design of the mechanical system in terms of controls, and how the opinions of the homeowners may differ greatly from my opinion as the consultant on what I think is best. So a good lesson for me. And I think that this all came about, our obsession with zoning. I think it came about when we started doing the whole dual zone in cars, right? Where it's like, oh man, somehow you can have these 2 knobs right beside each other, and there's some like invisible air wall between the passenger and the driver's seat. And like you've got yours cranked up 6 degrees higher than the other one. There's no way I believe that that's actually happening. But I'm blaming it on the car manufacturers, why we've got these high expectations in terms of controls in our homes. So that's one of the areas where we have been doing a lot of learning and trying to improve our practice is in helping understand customer expectations at the start, and then also working on setting customer expectations out of the gate, right? So something like, okay, if you want a system that's not zoned at all and you have a 2-story house, that's great. Just know that it's going to be a degree or 2 warmer on the second floor than the lower floor, and that's okay. as long as you know that that's not a bug, maybe it's more of a feature for you. Another thing that I'm just looking at that. We need to invent vent cooling beds. Hey, I remember my father talking about how they had a water bed back in the day, and you could like heat and cool the water bed, different sides. And apparently, I was like, the water bed was pre-me, but apparently, if you left the heater on the water bed off, it was very unpleasant, and it took like 8 hours to warm back up. So, would not recommend. But second theme I want to talk about, this is something where a lot of these learnings are coming from a passive house project that we've been working on in Winnipeg that was finished a number of months ago and actually just received its certification, which I think it might be the first certified passive house project in Winnipeg. I'm not positive, but if it's not the first, it's in the top first two or three anyways. So we've got some learnings from that project in terms of dealing with moisture in cold climates, and a couple other projects as well. So this is the passive house that just got certified in Winnipeg. It's called the Garfield Street Passive House. Super cool project by Montaigne Architecture is the architect on this one. And we got to play the role of passive house consultants. Some features of it. South-facing, so you've got lots of south-facing glazing. We have this big eyebrow above the windows to help kind of reduce the overheating in the summer. They looked at exterior shading in the summer, but they were able to, they needed a heat pump anyways, so they do have active cooling. They found that the cost was going to be pretty high, so they didn't end up doing exterior shading. What else can I tell you about this one? So yeah, it's a heat pump heating and cooling system with electric resistance backup. And it's got a heat pump water heater. And the envelope is all trusses filled with dense packed cellulose. So the roof, the walls, and the floor is all dense packed cellulose filled trusses. So something that was happening in the first winter of this project was some condensation on one of the windows. These are really good windows. I think they're Initech Defender windows. And one window in particular had some condensation showing up on it, which to me was very confusing because the passive house model did not flag that there was any condensation risk for any of the windows. And this was one of the windows that the model did not require heat beside because it's meeting the comfort criteria for passive house. So it's going to be warm enough to be comfortable without a heating vent beside it. So we didn't put a heating supply next to this window. It's in the kitchen. But they were experiencing some condensation. And one of the lessons that we learned on this was, first of all, this window has a lot of coatings on it, including it's got this Cardinal I-89 coating on the inside face. So it's a low E coating that's on the very inside surface of the window to just help boost its performance a little bit more and help it have a little bit higher R value. And what I learned since this project was that coating makes a window particularly susceptible to condensation because by reflecting heat very effectively, it cools the surface of the window even more than a typical triple pane window with low E coatings. And so without realizing it, by speccing these super good windows, we created a higher condensation risk. And because it's in its first year, it's just been constructed, there's still a lot of construction moisture. And so our interior relative humidity is probably a little bit higher than we can expect over the next few years, but especially this first year, it's going to be a little higher. So maybe instead of 30%, it's more like 35%. And then finally, the last thing we learned was that there was a blind over top of the window on the inside that was closed most of the time, and that was also dropping the temperature of the window. So we worked with the client and we talked about whether we should introduce some heat close to the window. And the client said, they would be happy to try just keeping the blind, up a few inches to start. And that was able to kind of solve the issue. But to me, the lesson that I learned on this one was, even if the energy model tells you it's okay, do recall that the energy model was made in Germany, which has the kind of temperature profile of Vancouver Island as opposed to the temperature profile of Winnipeg. So sometimes it's okay for a little bit of extra factor of safety when we're in these really cold climates, because it's pretty hard for a window to stay condensation free when it's minus 35 outside and you've got good indoor relative humidity. So another issue that we ran into on this same project was another condensation issue, was on the preheater. So because it's so cold in Winnipeg, Passive House requires continuous ventilation. And to do that, we need a preheater on most of the ventilation units out there. So this ventilation unit, it's a Zender, and it's got this nice little preheater to keep the air coming in at minus 10 degrees. So that'll prevent the unit from going into a defrost cycle and kind of stopping the flow of fresh air for a period of time. But as you can imagine, this experienced some condensation. So we did mention this at the outset, and it didn't get insulated initially. And so there was some condensation. Unfortunately, it happened right over the electrical panel, so made it a little bit more urgent to address it. But the initial fix was to, the initial fix here was to insulate the section that the ductwork went through. And we all thought, including me, we thought, okay, perfect, we solved the problem. So the contractor did a great job. He insulated this section with some Armaflex, went away, and they still had condensation dripping out of it. And what they found was it was actually condensation forming inside of the electrical box. Right here, you can see some ice actually building up even, because there was some airflow through this box. And this side is still really cold because it's not insulated. So the solution was to tape this box and make it all airtight, and then to insulate the entire box. So here was the finished product. And this did the trick. And so they aren't having any water dripping on their electrical panel anymore. But this was way more intense of an insulation job than I would have expected. And part of it is because my frame of reference for a mechanical room on the prairies is pretty dry. And this is a passive house. And so even though it's in a mechanical room, there's no people in here, it's a much more humid environment. So it's, maybe 30% relative humidity, as opposed to most of the mechanical rooms I find myself in are probably like 10% relative humidity. And so there was just a lot more moisture available. And so when that duct has any cold surfaces, especially when it's cold as minus 10, then it's going to start to condense in a hurry. This is a different project now. This one's about an hour and a half away from Regina. This was an existing house that was built maybe, I think it was 6 or 7 years ago. And the homeowner was having issues with condensation on their windows. So specifically in the winter, you can see there's like a lot of condensation going on this window, and it's freezing. It's creating some ice damming, and it was creating some mold behind the trim as well. So they were taking some trim off. I think they were unfortunately getting lawyers involved, but our client wanted us to assess what was going on, what the issue was. And they were figuring that it was the windows. There was the quality of the windows. They were poor quality windows in their estimation. And so that was what was causing all that condensation. So I did a bunch of work with them, reviewed a bunch of pictures, interviewed the owners. I was going to go do an in-person inspection. However, there was a blizzard bad enough to close the highways, and so we had to do a virtual inspection via Zoom, but that worked out pretty well too. And what I discovered was the windows were certainly playing a role, because they were triple pane as the homeowner had asked for, but they were kind of like the cheapest triple pane money could buy. So they were air filled. They didn't have any low E coatings or anything. So yes, the windows were cold, but the bigger problem was that the family was from US, the southern US, and they found it really dry in Saskatchewan. And they had a big old HRV in their house. Well, not old, but big new HRV in their house. And so when they ran the HRV in the winter, it dried out their house considerably. And they were not used to living in a cold, dry place. And so they were getting, cracked cuticles, they're getting nosebleeds, they were getting coughs. It was really uncomfortable. And so what did they do? They turned off the HRV. And they would only run the HRV when someone had a shower. So someone would have a shower and they'd run the HRV for 20 minutes and then they would leave it off the rest of the time. And so the problem in this house was not necessarily just caused by the windows. And it wasn't caused because the house itself was too humid, but because the house was too dry when it was running as it was designed. So it was kind of a puzzling one, but yeah, it turned out that having an HRV as opposed to an ERV, which would have kept it a little more humid, was what led to their condensation issues on their windows. So the lesson that I learned on this one is sometimes the obvious cause is actually not the full picture. And it was a really good lesson for me, or reminder in this whole thing that we all talk about, this building as a system approach, right? So this is the HRV that they had in there. And interestingly, the controls for this HRV will turn the unit off. You can set it to turn the unit off when the humidity, or to turn the unit on, sorry, when the humidity gets too high. But there's no setting on it to turn it off when the humidity gets too low. And so that was the issue that they were having. And then this is just a fun picture and slightly terrifying. This is what we're all trying to avoid in our projects. So this is not a project that we worked on, but this is a client in another capacity, and his condo, he moved out of this condo shortly after these mushrooms appeared. We asked if he tried any of them. He said no. And here's the zoom out. Oh, where's the zoom out? Yeah, here's the zoom out. So not surprising, it's happening right under junction with a window. So likely, my guess is air leakage, like some sort of poor sealing, air leakage in the winter, condensation, and then running back behind that drywall. You can see the molding's a little pudgy here too. So obviously some water going on there. So that's just a fun one. Only lessons learned here are don't eat the mushrooms in the carpet. Yeah, that's right. And it could have been bulk water as well. Could have been poor flashing or something on the window for sure. I didn't have any pictures of it because the gentleman didn't send me any, but he did say when they pulled back the carpet, it was pretty bad. Mushrooms were not the only things growing under there. Okay, let's talk a little bit about heat pumps. Okay, we're going back to the Saskatoon house and a lesson that we learned on the heat pump there, which was, oops, heat pumps work in really cold weather. So this is a Mitsubishi Hyperheat, so it is a cold climate heat pump. It would be sort of one of the most advanced cold climate heat pumps available. And here is a cold snap in January in Saskatchewan. So it's topped out at -38 absolute temperature. And this little red line is the heat pump compressor, and the green line is the electric backup. So you can see there's certainly a lot of electric backup happening during that cold snap. But interestingly, the compressor is still running almost the entire time. There's a couple periods where it turns off, but really the compressor is still running even down to -38. I will say this was slightly puzzling because according to the manufacturer, it's supposed to cut out at -27, not -38. But proof of concept, the compressor was still generating heat 10 degrees below where it's supposed to cut out. So for all the naysayers about heat pumps in really cold places, they do work. A few other heat pump learnings in cold climates. Question cuts out at -27 or COP is less than 1. On this particular unit, the COP is less than 1 at -27, but it should also cut out. It was that particular model is set to just like shut off the compressor at -27, apparently. So they did have to replace the board because it wasn't working. This is a project that we did in Saskatchewan. It's called the Dumont Youth Lodge. So it's a youth lodge and camp close to Batoche, so not too far from Saskatoon, Saskatchewan. And this is an all-electric building. So it's heated and cooled with heat pumps. It's got some heat pump water heaters, and it's a pretty good envelope. It's maybe like walls are R40, crawl spaces are 25, roof is R 80 to 90, somewhere in there. So it's quite a good envelope. And an issue that we had with the heat pumps on this one was ice buildup. So if any of you have done projects with heat pumps, especially in colder spots where you don't have a lot of thawing time during the winter, this can be a big challenge, is dealing with all of that condensate from those heat pumps. So this was sort of the perfect storm, the ice buildup on this particular project. And that's because, first of all, these heat pumps were on the north side of the building, so none of the ice had any chance to kind of melt or sublimate when we got some warmer temperatures. Second of all, is in a bit of a corner. And so what we realized was probably this wasn't just condensate from the heat pumps, it was probably also a snowdrift around these heat pumps that hadn't got cleared away as well. So there's maybe a bit of a maintenance issue in there as well, but certainly a consideration for us on future projects in terms of design. And so part of the concern was, are they gonna, is it gonna wreck anything or have any moisture wicking up behind siding or anything like that? And this is what the heat pumps looked like when we did our inspection. What I don't have a picture of is, so these are on another side of the building, but the ones on the back look very similar. What I don't have a picture of is what they look like when they finished grading around the building. And they'd actually graded up to like halfway up these stands. So we had said, hey, make sure you put them on stands so they can drain out freely. And then they added a bunch of fill. And so our nice 1.5-foot stands became, like 6-inch stands or something like that. So that was part of the issue on that one. And so what this particular client has requested, and what we give everyone the option now of when we're working on projects like this, is you can either drain condensation onto the ground, or you can have a heated drain pan with a pipe going back inside the building and some heat trace and insulation, and you can drain that condensation back into the building to a drain. So that's going to be more energy use. It's going to be some more effort in terms of detailing, but depending on the project, if you want sort of like a zero maintenance solution, or if you've got a place where you really can't afford to have any ice buildup, then that's a good option. Okay, back to the Winnipeg Passive House. This was a lesson learned on this one. We had not specified, we had said to locate the heat pump 2 feet off the ground. We had not specified on a stand, but we had in our drawings, but then when we were asked about, we recommended, hey, we recommend this put on a stand. However, it ended up getting put on some brackets. And in fact, Mitsubishi makes these brackets and sells them for hanging their heat pumps. Turns out they work really well in Asia, where you have concrete buildings, but they don't work very well on wood frame buildings, where if you get a heat pump that's got the right frequency for that wall, it's going to create basically just like a huge speaker inside the house. And when that house is a passive house and it's super duper quiet inside the house, that's a big problem. So that was one of the first things that the occupants noticed, is that the heat pump was really loud and it sounded like it was coming from everywhere. And this was right on the other side of the living room. So as you can imagine, that did not go over very well. And so the first issue was that they put some vibration isolators on this heat pump. So you can see these little pads on the heat pump legs, but a vibration isolator needs to be much bigger than that for low frequency sound. So this is like a fraction of an inch thick. You would need probably more than an inch, a couple inches thick, in order to prevent that vibration. And the other issue is that even with that big, if you have a big isolator on there, it's just still going to always create some vibration translated through the wall. So what happened was they put some bigger vibration isolators on in an effort to make it work, and it was better, but it still wasn't quiet enough. And so you can see this is in the tracking software from the contractor, hasn't completely resolved, so it needs to be put on the ground. So that's a good reminder. It's something that we always recommend as a first kind of option, is always locate a heat pump on the ground, especially with wood frame buildings. It's less of an issue if you have a commercial building where there's always like background sounds happening, but if it's a home for sure where people are sleeping or expect a little bit more silence, then that can be a challenge. And then my last heat pump project to highlight is this project. This is one of Justin and Element Construction's projects, one that we're super excited about. It's pretty awesome. And I'm highlighting this because it actually doesn't have any heat pumps in it, which is cool. So this is a kind of it's not a certified passive house, but it's certainly very much inspired by the passive house principles. And how we got away without a heat pump for heating and cooling is you can see the glazing on it. This is facing south, all has exterior shades. All of this glazing on the west side, this is like a sunroom. So this actually isn't part of the thermal envelope. So we've just got windows on the south, and they've all got these exterior shades. And so we're able to exclude a lot of solar heat gain, so we don't need a lot of cooling. And so the solution that we were able to use for cooling was we've got this ground loop that Zender makes called the Comfofond. And it doesn't have a heat pump, it just has a pump and brine going through this loop. And then it's got a coil, your fresh air comes in over that loop and then gets distributed through your house. So no compressors, just a pump and some water and some glycol. So kind of a cool solution. And here's what it looks like in this project. So it's very passive inspired, as you can tell. This is that Comfofond. So we just have the brine loop coming through. Here's the ERV. So it's spreading that cooling around the house in the summer. And then the Comfofond also can preheat the air in the winter. And then it's got a little post heater in the winter on the ventilation air as well. So this was a cool project that I thought it was neat to see a project get so efficient, even in Saskatchewan's cold climate, that we could get away without a heat pump in the heating and cooling system. So I thought it'd be funny to end the heat pump section with a project with no heat pump in it. Okay, my fourth theme is called Not Just Good on Paper, and this is something that we've been trying to get better at. So a lot of our focus has been on, hey, how could we integrate envelope and mechanical and make sure we're designing something really good? And now we're realizing that we need to focus more on, especially in the residential market, how do we get that really good design from the paper drawings to the built environment? Because there are pretty good processes for this, though, there's always issues, but there are better processes for this with a commercial building where, as an engineer, I have to sign off on a letter saying, yes, this building was built as per my design. So the owner has to get me to inspect their building and be happy with it before I provide that sign off. On a residential project, that's not the case. So often what happens is we give a set of drawings to a client for a residential project, we never hear from them again. And so we actually don't know what's happened. Has the building team understood our drawings? Were we clear? Did they understand and kind of realize how it's all supposed to work together? And so the next few lessons learned and examples are some ways that has gone really well and some ways that has gone poorly on some of our projects. So here, this is at Winnipeg Passivhaus. You can tell this was top of mind and put a lot of time into it recently. One of the challenges on this one was we specified instead of a plumbing stack, or instead of a 3-inch plumbing stack as you normally have, we specified a really tiny 1.5-inch plumbing stack just off the kitchen, and then an air admittance valve on the 3-inch stack. And this was based on some research that Passive House Alberta did, that Frank Crawford was involved with. And we proposed this to try to reduce the thermal bridging of that plumbing stack because we were really close to the line for Passive House certification. So we put this on the drawings. We made a very clear note on the drawings. We gave the architect a letter of like an alternate solution to the building code, sealed with an engineering seal saying, here's our letter proposing this alternate solution. This is how it complies with the building code. Here's the research to back it up. Great. And then we get the inspection pictures back from the team, and the plumber said, oh yeah, we didn't do that because that doesn't work by the building code. We never do that. And so they ended up putting in the same stacks they always put in. So then we had to go through all this effort to try to find other places to reduce the heat loss out of this home because we really needed the heat loss that that plumbing stack was contributing to in order to certify. And I realized that while we had done a good job of communicating this design approach to the design team, nobody had communicated this design approach to the plumber, aside from handing them a set of drawings, which asks them to do something that they'd never done before and that they knew was against code. What they didn't know was that there was an engineering report saying, here's our alternate solution, here's how we're going to comply with code. So that was a really good lesson for me in terms of how do we bridge that gap better between the design team and the construction team and make sure that we're all pulling together. This is another example of this. In the same project, we specified these really nice April air filters. Indoor air quality was really important on this one. And so we've got 2 filters. One is for the regular, one's for a pre-filter, and the second one is for a really intense MERV 16 filter for wildfire season. So the second filter box would remain empty until there's a wildfire, and then you shove a big 4-inch MERV 16 filter in there to reduce wildfire smoke in your home. And here's what ended up happening. Turns out the contractor wasn't able to get the April air filters that fit in with this rack. And so they bought these premium April air filter racks, and then they modified them and shoved cardboard Filtrete filters into them. You can see this one's already bent. So obviously this was not a good solution, but we could have had a little more dialogue between the construction team and the design team on, hey, I can't get those filters. Can I put in a different filter rack instead of the April air filters? Great, let's do that, as opposed to putting in the April air filter racks and then putting a different filter in. So another good example of kind of communication. This is a different project. This is one that's going for, this is in Winnipeg. It's a sort of an interpretive center, and it's going for Passive House certification. This is not a project that we worked on, but I presented on this with a panel in Winnipeg a couple months back at a mechanical contractors conference. And something that I heard from a bunch of the mechanical contractors that worked on this project that I thought was really fascinating was about 4 of them brought up the fact that the duct work that they had to do was so tight. Like the space they had to run their ducts and their pipes and all of that was so tight. None of them mentioned that it was like, that the Passive House aspect of it was challenging. The thing that was challenging was the fact that they didn't get enough room to put in their ductwork. So a good reminder that even if it looks good and works on paper in the CAD program, there's somebody still has to fit their hands in there to like put the duct in. So that's something that we're always working on when we're working on high performance projects, is working with the construction team too, to say, hey, how can we make your life easier as opposed to more painful when you're trying to make our designs happen in the field. And a place that we've had some really good success with that is we've done a ton of work with this company called 320 Modular out of Saskatoon. So they do mostly commercial modular buildings. So they'll do like school portables, they'll do First Nations band offices, they'll do multi-unit residential buildings, and they've got an integrated design and construction approach. So often they're bidding a design build for their projects, and they will stick with the same team. So we've worked now on, I think we're over 100 projects with them, and their mechanical contractor is the same contractor every time. And so we know everyone on the mechanical team. We know all of the designers in 320, and there's a lot of phone calls that happen. And the great thing is, because we work on these projects over and over together with the same team, we get to iterate, right? So if we do something on a project, we're talking with the mechanical guys and saying, hey, how did that work? Were there parts of that that could go better? Were there parts of that that you really liked? How can we make sure it's better on the next one? And then when we build the next band office or school portable or what have you with that team, we can make sure that in our design drawings, we're incorporating some of the feedback from the construction guys on what they liked or what they didn't like. So that's been a really cool partnership that we've had over the past few years. And it's really informed our design practice for some of our other projects too, because frankly, we're all busy, right? You know, contractors are busy, mechanical consultants are busy, architects are busy. And so it can be hard to close the loop and sort of come back and revisit a project and say what went well and what didn't. But when we've got active projects going with this group, it's much easier to do that because we can, on the next one, we have our design meeting and we say, hey, what about the last time? Did this work? Do we need to modify anything? And then here's a project where things frustratingly did not go quite as well. We sent off this schematic drawing. This is a single family home. We specified an ERV for the ventilation. We said we want an ERV. Here's the model number. Here's the size. Put in an ERV. And the mechanical contractor came back and they said, here's the HRV that we're going to supply. And we said, nope, we want an ERV. And they said, nope, we're not going to put an ERV in. We're going to put an HRV in. And so I sent an email, which I thought was diplomatic, and included in there, I said, my understanding experience in our climate is that best practice is to install an ERV. I'm concerned an HRV will lead to indoor humidity that is too low in the winter and potentially too high in the summer, et cetera, et cetera. So interestingly, the mechanical contractor said that he was concerned that the ERV would lead to condensation on the windows in the winter in this project. He also told me that he's been installing HRVs for 20 years and he's never put an ERV into a house. So at that point, I was a little bit confused because I was unsure how he both was very positive that ERVs were bad, but also had never installed an ERV ever. So it seemed like those two were maybe not compatible with one another, but that was the case. And so, yeah, this was a challenge. We went back and forth with the builder and the contractor, and we talked to the client. And at a certain point, we said, hey, like, we can't make you put in an ERV unless the client is going to back us up on it. And the client said they don't care that much. And so they're putting in an HRV. So that was a little hole in my heart as a consultant because the client is paying us to advise them on best practice. And ultimately, we weren't able to successfully have best practice sort of enacted in this project. And we're going to come back to this in the final section, but that's where I'll leave it for the moment. So I've got a picture here of what paradise may look like, especially if you're from a cold country like Canada. So this could be what paradise looks like. And my question is, at the end of this section, how do we get closer to our amazing buildings paradise? And I do think that a big piece of it is continuing to work on communication between design and consulting teams and construction teams, and then feedback back up the up the ladder. So I know lots of times in high performance buildings, we're talking about integrated design teams, and I think that's great. I think that makes a big difference. That brings me to our final topic, which is how to think again. So I read this book last year called Thinking Again or Think Again by Adam Grant. And it's all about how do we not get stuck in a particular idea and refuse to change our minds even when we're wrong. So that's sort of the thrust of his book. So the first part is, how do you personally, as the reader, not get stuck in a certain idea which may be wrong? And then the second part is, how do you help, how are you more effective in convincing other people that they might be wrong on something if they're stuck in a certain way of thinking? So this is one of the figures that he has in the book. He talks about the overconfidence cycle, how we can often get into this cycle where we've got a conviction and we end up with some confirmation bias. So we only read the things that support our conclusions. And then we figure, oh, that's validation of my conclusion. And then we become even more proud at how right we are. We just kind of roll around the loop. And he talks about, as an antidote to this, the rethinking cycle. So how can we be more humble about our positions? And how can we embrace doubt, look for curiosity, and then discover that maybe there's more to it than we thought? So a couple of the sort of things that he highlights that can help us move from overconfidence to rethinking, and I'm applying this to myself in this coming up example, is we can look for areas of agreement and we can concede when we think someone else is right. We can support our own arguments with a smaller number of compelling examples, as opposed to just like, my tendency is always just to say, hey, I've got 10 examples to show you of why I'm right and you're wrong. Turns out that's not very effective. We can also ask genuine questions. So as opposed to trying to just like trumpet our own opinions, we can ask questions about others' opinions. And then finally, if required, we can discuss the process. So a line that he used that I really liked in the book was, how can I change your mind? Is there any evidence that I could give you that would help you change your mind on this? So I'm going to revisit my last example that I was talking about, the whole ERV, HRV thing. So I ended up sending this email to the contractor. I said, okay, I think I understand. So it's not that you've had any bad experiences with ERVs, and more that you've not had the chance to work on any projects where an ERV has been used. Is there anything I can do, or information or examples I can provide, that would make you more comfortable with the operation benefits of an ERV? And the contractor said, no, I would like to move forward with an HRV. And then there's maybe a little bit of frustration or annoyance. At least that's what I'm reading into, is I mentioned this a long time ago. Thank you. Which for me was actually quite helpful, getting this response, because I didn't have to spend any more time trying to convince him, because what he was saying to me in his response was, no, I will not be convinced. So case closed. And what that brought me to in this particular case with this client and this contractor was a bit of a rethinking cycle of how I approached it. So what are some of the things that I did that might have led to him being closed to the idea of trying out something new? And some of it's beyond my control, but I realized at the outset, I did express some frustration to the general contractor about the mechanical contractor. And I said, oh, the mechanical contractor, he's just doing the thing he's always done. And I think that maybe rubbed the general contractor the wrong way, because he probably thought, hey, this paper pushing engineer is coming in here and telling me how to build this building and telling the mechanical contractor how to build this building. And so I think that the way I approached it initially got his hackles up a little bit right out of the gate. Also, I didn't do a very good job of listening at the start when I was trying to express why we had designed with an ERV instead of an HRV. I told him why an ERV was good, and I didn't listen to what his concerns were about why an HRV might be better. And then finally, there is conflicting evidence out there. And there are times where an HRV is better. So I thought this was really funny. Here's AI for you. So I Googled and used the AI overview and I said, first of all, ERV better in cold climate, question mark. And AI told me, yes, an ERV can be significantly better for a cold, dry climate like Saskatchewan's. Oh, it even knows where I live. That's creepy. And then I said, HRV better in cold climate. And AI told me, yes, again, yes, a heat recovery ventilator is often the superior choice for cold, dry climates. What do you know? And they've got references they're citing. Turns out they cite Life Breath both times. So Life Breath is just crushing it in terms of search engine optimization, but not in terms of consistency on which is better in a cold climate. So I needed to acknowledge that this is a complex topic and there's conflicting advice. So I went through this rethinking cycle and I realized I was frustrated with the outcome of this particular project and the fact that I had to back down on my recommendation and the contractor didn't want to listen to what I had to say. But there were some things that I could have done in my approach. I could have been less adversarial and a little bit more understanding of where the contractor is coming from as well. So, in conclusion, one of the big lessons that I've been learning about building science, whether the paradise we're moving towards looks like a white sand beach or whether it looks like a building that's so efficient that it doesn't even need a heat pump, just has a single ground loop. I've been learning that communication and working together and like learning some of those, the art of how to do integrated design is maybe just as important as some of the hard building science lessons as well. Because if I can't do a good job of communicating that building science and helping sort of the other people in the project team feel like they're part of this goal of working towards a better building, then it doesn't matter how many lessons I personally have learned in terms of making a better building. So thanks. That was really high level. It was kind of a little few bits and pieces of different places, but I hope that you enjoyed some of the lessons that our team has been learning, some of the things we've been trying out, and I hope that you enjoyed some of the pretty pictures and lack of bullet points as well.
I'm going to jump right in and I'm going to say, as soon as Justin has his voice back, we've got to get both of you back and we got to talk about ground loops and Zenders and how we're going to solve all of our energy issues that way. Because I think that's
Sounds good to me.
an excellent topic. But yeah, thank you, Matt. Absolutely. This has been amazing. And for some of us, it is actually a very high level. One of the key things that I picked up along the way here was that your energy model on one of the projects was 13% off from the occupancy. And actually, I think that's actually a pretty tight number because how do you know how people are going to use your building? You
For
can
sure.
model
Yeah.
everything, you can model whatever you want, but you have no idea what that occupancy load is actually going to look like once people start to use that structure.
Yeah, absolutely. And I will be the first to admit that looking at that table, there's a little bit of luck there too, because there's some of the individual numbers within that 13% were like way over and some were way under and they kind of balanced each other out. But yeah, there's certainly you don't always get that close, that's for sure.
Well, I thought it was pretty good. And kudos all around. I'm just checking to see if there's any questions in the chat that you may have missed or I may have missed. But now is typically when we open up the floor for questions. And so if anybody has a question while I'm just scrolling back through, please chime in.
I'll jump in.
Jeremiah,
Sure.
you are up.
That was great. Thanks, Matt. That was really well delivered and a really good sort of breakdown of all the different sort of components working through a project at that level. So that was awesome. I had a question, kind of goes back to near the beginning on, I think it was like slide number 17, where you had some condensation on one of the windows where there wasn't heat near, no heat was sort of determined to be needed near that window in the model, but some condensation still formed. In situations like that, like where an energy model may not show the need for heat to be located or close to a cooler, potentially cooler surface like that. What about having ventilation air, assuming a ventilation system is independently ducted from the heat system, having ventilation air moving in an area like that just to help move some of that air around? Either, I guess it'd be, even if it's supply air, just moving something past that.
Yeah, for sure. That would certainly have been helpful in this situation. Yeah, definitely. Like any air movement past that window is going to help just disrupt that little bit of a cold kind of film of cold air right in front of it,
Mhm.
and assist with that. And we probably in this particular case relied a little too heavily on the model telling us we didn't need anything there, rather than being on the safe side and saying, let's put a little bit of supply air
Right.
close to that window too.
Yeah. Cool.
And I think part of that is the challenge of like really wanting to follow the passive house goals of simplifying the mechanical system, because you want to say, hey, how many supply diffusers can we get rid of? How much ducting can we get rid of to really simplify this mechanical system? But in a cold climate, it just gets hard because you have so many windows that still require heat by them that it starts to kind of look like just a typical mechanical system, to be honest.
Right.
Um, so, so yeah, we're always struggling with that balance of how do we simplify things, but also make sure that we're kind of making sure that we're appropriately designing for the extreme conditions that we can find in a place like Winnipeg.
Yeah, that makes sense. And just one more kind of doesn't follow that one, but just one other one that I was thinking of as you were talking about the family who had some issues with their HRV because they were coming from a warmer, maybe more humid climate and not quite used to being dry here in the wintertime. When it comes to ventilation, like designing ventilation rates into projects, obviously there are sort of ventilation standards that suggest the rate that the house should be ventilated at based on occupancy or square footage, or depending on sort of what program that you're using to determine that. But do you often, or do you ever look at sort of setting the ventilation rate just based on the occupancy of the actual house versus, like, I think of sometimes, like, we just finished a house that's 3 bedroom, 2,100 square feet, and it's only got two people in it. Like the occupant or the ventilation rate that it, is suggested to have is, I feel, higher than what it probably needs to have based on who's actually in it. And I think maybe in certain situations that rate could be changed a little bit, and then maybe also help with discomfort if it's, bringing in a lot of extra dry air at certain times of the year.
Yeah, for sure. That's a huge kind of factor is, yeah, how heavily occupied is a house, and you can go all the way from a big custom home that's got two people living in it and both work outside of the home to a more modest sized house with a large family that's, everyone's home all the
Yeah.
time. So that makes a huge difference in terms of how much ventilation air you need and how much humidity is being generated as well and needs to be dealt with. So we've also found that it can be easy to over ventilate on some of these, some larger homes that have fewer occupants in them. So one, I mean, code gives us some requirements around what the capacity of the ventilation system has to be. We can do some things too with like CO2 based controls too, to say, hey, if CO2 is okay, then we're going to ramp down the ventilation until CO2 starts to rise, and then we're going to ramp it up. And that can be one strategy to help with that.
Yeah, makes sense. Thank you.
So Cody had some questions. I don't know if Cody, if you want to join us and just ask your questions. They're centered around the house without a heat pump. Give Cody a second here, see if he wants to chime in.
The first one was about the ductwork in the picture, it looked like the takeoff was at the end of the trunk. I don't know if there was something I'm missing, or if to me that would not allow the trunk to be pressurized, so the airflow would not be evenly distributed down each branch.
Was that was when I had the comparison of the two different houses?
Correct.
Yes. Yeah, there were definitely some space limitations there, and that was not an ideal duct configuration. You are absolutely right. So yeah, that was a bit of a challenging duct routing just due to some space configuration. So we were relying on some dampers there to help out with the fact that it was not the way that without space constraints would be ideal for sure.
Like Aaron, I'm curious about the house without a heat pump. How big were the ground loops? And I know that like if the loop is too long, it requires too much energy to push the brine through. So was there multiple loops?
That's a good question. It was my colleague Stefan who did the loop design, so I'd have to ask him. I seem to recall that it was like a 400 or 500 foot loop-ish, and I believe it was a single loop. So I think it's sort of a horizontal, like slinky style loop. Um, but I would have to, that's like 400 or 500 feet is me going off of
Yeah,
memory
Justin
from
said
years
500
ago.
feet.
So, okay. Oh, wow. I did pretty good.
Yeah, thank you.
Thanks, Justin. So that we're actually looking at doing some instrumentation on that house. So we're going to be putting in an energy monitor, and then also we want to put in you can get a component for the Zender that allows you to log the temperature of that loop and log the temperature of the incoming and outgoing air and the flow rates and stuff. So we're hoping to get some of that rigged up later this summer so we can see how the system's performing, because it's a new one for us. So we're excited to see how it's all working.
Very cool. Well, I know we're getting close to your hard out, Matt. We're not quite there, but I think we need to have you and Justin back in the future to talk just about ground loops and Zenders and how to avoid heat pumps in a cold climate.
Sounds good. Justin, you'll have to get your voice back between now and then, I guess.
I just want to share something quick. Matt, that's great. Really lovely to hear both upfront how you assess client expectations and comfort, and then you're learning from each project, you're debriefing with your team, kind of be a bit of a circle and a loop to get better, because we're all experiencing new products for the first time, or new enclosure, but also new expectations. I think there is something quite interesting around PHPP is a really effective model, but you're presenting and sharing that like PHPP rather isn't the person who lives in the house. So passive house planning package might think 25 is comfortable as an upper limit for cooling. But I was sharing this with someone else the other day that said 25. No, I keep my house at 21, or my wife likes it at 18. And I think it is important to check with your clients, like, what is your expectation of comfort? It is a big part of our sales pitch now about building better, right? More durable, more comfortable, more resilient. And that comfort piece is so subjective. So I really like that. You asked those questions. I'm reminded our house, we had Zon Engineering in the East help us with our project, and Greg Laskin was still involved there. And I remember him asking me a question, getting down to ventilation requirements. He asked us, like, what do you cook and how much do you cook? And I thought he was just really getting really personal. And what he was asking was, how much are you boiling? So I can understand, do I need to consider getting rid of that with a dedicated hood? Or can we look at some kind of recirc? And if those kind of questions that aren't addressed by typical models, they make assumptions, right? Average cook rates per day, and that was well below what we do. And I think it does, kind of make you really informed with your team. I think that's really a smart tool, and I can take that away because we all build for different people initially, right? Initial occupant, has say to what that house looks and feels like. So thanks for sharing that.
Yeah, thanks. Yeah, and it's interesting to me too how much sometimes like things that I know are are just part of living in a high performance building, I take for granted that the client knows that and they don't always know that. So for example, like if you were used to, I'm sure some of you have come across this, if you're used to a house with a big old noisy bathroom fan. You take a shower, you turn on the bathroom fan, it just sucks all the moisture out right away, and that's it. And your bathroom fan works great. Versus you have a high performance home, it's got an ERV, and you have a shower and it's really steamy in the bathroom for 30 minutes as that ERV slowly chugs away and takes the humidity out of the bathroom. And that's not a problem, but it's just different. And so if you grow up thinking that an effective ventilation system has to remove all that humidity instantly with a big exhaust fan, then when you move to that high performance mentality of, oh no, low and slow, like we've got this ERV, it's going to dry the room out, but it's not going to be in the next 2 minutes, it's going to be in the next 30 to 60 minutes, then all of a sudden that becomes a, like, if that's not your default, it becomes a, oh, something's wrong, as opposed to, actually, no, it's working just the way it's supposed to. So that's something that we've been learning too, is to try to express to clients when they might experience something different than they're used to, so that the first time, the first week in their new house, they're not like, oh no, the bathroom's not, it's full of moisture, like something's wrong.
That's awesome. And it boils down to, are you an active participant in your house? Or are you just, you know, are you a byproduct of that structure? And then your threshold of knowledge, or
Totally.
how much do you care? Because, if you're just need to go about your day and you don't care how the building functions or want to be part of how the building functions, then part of our job as a builder or a consultant is to make sure that those systems are in place, that the structure will be just fine whether you are there or not there.
Yeah.
But if you're going to push the button to kick the ERV into high gear when you get into the shower because you're an active participant, then that's cool.
Yeah, totally.
Overall, I really appreciate your time, Matt. And anytime somebody brings car manufacturers to the show, I love it, because they are killing it on expectations and warranty. And us as builders, even though individually we're doing a pretty darn good job on expectations and warranties, the industry itself is not in the same league as car manufacturers. And that's why people want their 21 degrees.
Yeah, totally.
All right, if there's nothing else, I'm going to wrap this up. Thank you very much for joining us for another amazing episode of BS&BEER Canada. Matt, I hope to have you back with Justin. I'm going to say 2027, and we're going to talk about ground loops and Zenders. Until next time, everybody.
Awesome. Thanks for having me.
Thanks, Matt. Thanks, everybody.
Thank you,
Thanks,
Matt.
Matt.